Hey folks, welcome to another edition of Flipping Physics, where you're going to learn the stuff at home watching videos, all right, to help you with the book, help you with reading and doing research on the internet, so that we'll either have time in class to actually do the problems, or if you're taking this online, it helped you read the book and understood the homework problems that you were going to do. So today, what we're going to do is actually, hopefully, take all that stuff you learned in calculus class and finally make sense out of it. You know, you learn all this stuff in calculus, and Isaac Newton and the boys invented calculus just so it would make sense with motion. So let me give you something you might have seen in calculus class. You might have said a particle is moving along the x-axis as a function of time with the following equation. It came out to look like this. It was 3 plus 4t minus t squared. And this formula, this quadratic, described the motion. Today we're going to look at what you might have seen in calculus class and realize that Isaac Newton and the boys invented calculus so that you can do it and apply it to a physics problem, a real-life motion problem. If this is describing the motion, and you didn't have your graphing calculator there so you could see it, how would you describe what this thing is doing? And this is the beauty of it. Those kinematic equations kind of reveal it to you. So let's take the derivative of this. Let's take the first derivative. Let's do dx dt. What does dx dt give you? The instantaneous velocity as a function of time. Okay? And that gives you, if you take the derivative of the 3, it's a 0. If you take the derivative of 4t with respect to time, you just get a 4. And then if you take the derivative of this, you get minus 2t. And that's the equation for the velocity at any given moment. All right? Well, if I try that again and take the derivative again, dx, the second derivative of there, which is the first derivative of the velocity, it gives you the instantaneous acceleration. What's the acceleration at any given moment? And in this particular case, because we started with a quadratic, the time goes away. The 4 goes away, time goes away, and you get 2. And if you do the units, it might be meters per second squared. So you actually get a constant acceleration when you see a square term up there. Okay? If it started with a cube, you would still have a time-dependent acceleration. We'll talk about that in a minute. But right now, let's use a constant acceleration so that we can kind of understand things. Look at how elegant what you learned in calculus class applies to this. Stare at this for a second. This original equation, 3 plus 4t minus t squared. What does that mean? All right? Well, let's describe the motion. Okay? I'll tell you what. Let's make this chair the 3-meter mark. Let's make this the origin. So, at the origin, I didn't start my clock yet. I start my clock at the 3-meter mark. And then I'm moving instantaneously how fast at 0 time? And the answer is I'm moving at 4 meters per second, and positive will say is to the right. Okay? Follow this logic here, guys. Where am I when time was 0? Put 0 time in there, put 0 time in here, and you get 3 meters. So where am I at t equals 0? 3 meters. How fast am I moving at 0 time? Look at this second equation, and you'll see that at 0 time, I'm going at 4 meters per second. Got it? And then, what's the acceleration? -2. I am slowing down by, and I don't want to really say slowing down by, but I'm changing my speed by 2 meters per second to the left. If to the right is positive, I'm changing my speed to the left 2 meters per second every second. All right, so here goes. See if you can follow this. I'm going to be moving a little faster here. Back here, the clock's not started yet. But the minute I pass here, I'm going 4 meters per second, and after 1 second, I'm going 2 meters per second, and after another second, I'm going 0, and now after another second, I'm going negative 2 meters per second, and then when I get back over here, I'm probably going negative 4, and then when I get over here, I'm going even faster than negative 4 when I get back past the origin. Can you visualize? Isn't this cool? You could look at this equation, and I could run it, and actually, you see me going, and that's my motion. That equation corresponds to a real particle moving along the x-axis. Isn't that kind of neat? And that's calculus that gave you that stuff. That's probably what you learned in calculus class, but now it means something because, guys, look. X final equals X initial plus V initial times time plus 1/2 AT squared. 1/2 of A is -1. What number half of that is -1? -2. Isn't that sweet? You could look at the original equation and know where am I at t equals 0, how fast am I moving at t equals 0, and my acceleration. Isn't that cool? So you can actually look at that thing again. Let's see this equation. You recognize this equation? V final equals V initial plus AT. That's equation B. That's equation D. And they just appeared when you were doing this original equation. Something else you learned in calculus class. Maximum, minimum problems. Remember that? Okay, so if I throw something up in the air, the question is, when or what time was it when it reached the maximum displacement? What time was it when it went the farthest away from my hand? So if I throw this up in the air, and I'm saying, how high did it go? What am I really asking? When was it the maximum distance away from my hand? You hear the word maximum? I said about 5 times. Hoping you remember in calculus class that there was a way of finding a maximum. You take the derivative and set it equal to 0. That's what you robotically do in calc class. Now, you're in physics. Now you know why you take the derivative and set it equal to 0. People, if you take the derivative of displacement, what do you get? Velocity. And when was the displacement a maximum? When the velocity was 0, when it stopped at the top. Isn't that cool? So you take the first derivative of displacement and you get velocity. What if you stick 0 in for the velocity? That's taking the derivative and set it in the equal to 0. It gives you the maximum. So you take the derivative of displacement, you get velocity. Then set it equal to 0, and you're saying, when did it stop? And the answer is, when it was the farthest away. Let's do this horizontal thing again. Follow me with the camera if you can. Here we go. Passing the origin going 4 meters per second. Passing the origin going 4 meters per second, and I stop over here, and I turn around. When was I the maximum distance away from the origin? The answer is when I stopped. So you take the first derivative and set it equal to 0 because that's when it stopped. I'm the farthest away when it stopped. So if you put 0 in for the velocity, move this over to the other side and you get 2t equals 4. Then you end up with, I'll be damned, what a surprise, time equals 2 seconds when v equals 0 and x equals maximum. Isn't that sweet? Everything you learn in calculus class hopefully makes a little sense now. Okay? So you take the derivative and set it equal to 0, and you find out in this particular example, after 2 seconds, it stopped. So now you know 2 seconds. Now go back to the original equation and stick in 2 seconds over here and 2 seconds over here, and you get 3 plus 8, that's 11, minus 4. What's 11 minus 4? Okay? 11 minus 4 is 7 meters, right? So what's the maximum distance away? 7 meters. Did I do that right? 11 minus 4. Okay? So how far away from the origin was it at 2 seconds? When it stopped, 7 meters away. Okay? It was going 0 at that time. I love it. How much time did it take to get back to the 3 meter mark? Well, it took 2 seconds to stop, right? 2 times 2 is 4. 4 minus 4. It stopped after 2 seconds. After another 2 seconds, what's the velocity? Let's try it. What's 4 meters per second minus 2 times 4 seconds? Minus 4 meters per second. What does that mean? That the velocity after 4 seconds is right back at the chair. Here we go. Moving this way at 4 meters per second. After 1 second, 2 meters per second. After 2 seconds, stopped, 0 meters per second. After another second, changes by 2 meters per second, negative 2 meters per second, and the radar gun says minus 4 back at the origin. Isn't that friggin' cool? Okay? Let's try it again. What time t was x 3? 3 minus 3, 0. Move that over to the other side, and you get t squared equals 4t. One of the t's cancel, and t equals 4 seconds. So it got back to the origin after 4 seconds. We just proved it. Okay? Now, when did it go to the origin? Follow me again with the camera, see if we can do this. Here's where I didn't really start. My clock started when I was here, 3 meters away. 1 second, 7 meters away there. Back over here, and then over here. What time did it take to get back to the origin? How long did it take to actually get back to the origin? All right, so check this out. Get back to the origin. All right, so the time it took to get back to the origin, that means 0 equals 3 plus 4t minus t squared. That looks like a quadratic formula. Let's try that one. Move it all over and you get positive t squared minus 4t minus 3 equals 0. Now you can think of any two numbers multiplied together. Maybe we don't have to use the quadratic formula for this particular one. I made these numbers up, so I'm just going to get lucky, I hope. What two numbers multiplied together give you negative 3, but added together give you negative 4? Is there two numbers that do that? Multiplied together give you negative 3, but added together give you negative 4. And the answer is, I don't think so. Okay? So use the quadratic formula for this, and it's minus b, which is positive 4, plus or minus the square root of b squared, which is positive 16, minus 4 times a times c, negative 3, all divided by 2 times 1. And that would give you the time when you were at the origin. See, you stuck 0 in for where are you? And then we're looking for the time when I was here at the origin. The time I was at the origin. So I figured all that out, and I got 4 plus, so that's say 16 plus 12. Okay? Take the square root of that. 4 plus or minus that, all divided by 2, would give me my times. And you'll notice something really cool. You get two roots for the thing. So real quick, let's figure that one out and see what we come up with. Okay, I took a little pause and wrote down that it was 4 plus or minus all that stuff on the indeterminate is square root of 28 all over 2. If you try the numbers out, you end up with a time, if you make it a plus, of 4.646 seconds. And the other root that you usually just throw out in math class when you get something stupid is 0.648 seconds. So those are the two roots. The negative root you usually throw out, and the positive root is the one you really care about. So let's see if we can visualize what that just did. I started my clock when I was right here at 3. Start the clock. After 1 second, after 2 seconds, I stop. After 3 seconds, I'm coming back. After 4 seconds, I pass. And at 4.646 seconds, I'm back at the origin. The original origin, the 0 part. Okay? Now, what's this negative root? Physics class, you don't have to throw out negative roots. You learn some cool stuff from the negative roots. The negative roots is the time when I was at the origin again. But negative time means time before I started my clock. Isn't that kind of cool? It's like a number line where 0 is when you start your clock. Now go back in time. If I was decelerating, watch this logic now. If I was decelerating -2, and I was slowing down, and now I'm going 4, then I must have been going faster than 4 back here, because I was slowing down to get to here, and now I'm going 4. So if I backed this up and figured out what velocity did I have back here at that time, I would actually get a velocity that's greater than 4 that I was moving when it was back over there. It's really elegant to see that the other root really means something. Okay? Because I had to slow down for 0.65 seconds. I had to slow down to get to 4 meters per second when I started my clock. Isn't that kind of neat? So I wanted to show you that because there's some questions I could ask you now on tests and homeworks and stuff like that to see whether you really understood it. And that would mean I would ask you a question like, looking at these equations, when was the velocity a maximum? And that doesn't make sense for this question because the velocity is a maximum at infinity time. It just keeps getting faster and faster. But backwards, you're going backwards. The velocity will be a big negative number after 100 seconds, right? Well, I might ask you, where is it when the velocity was a maximum? We did that one. But if I give you a question that's a little bit more challenging, a question where the acceleration is not constant. So if you get x equals, let's say, 4 plus 3t minus 5t cubed, it's not a quadratic. Things are changing, and you might find when you take the second derivative, let's try that, dx dt, which is the velocity at any given moment, would be 3 meters per second, okay, minus, and then remember how to take the derivative of this? So that would be 15t squared. Oh, this is going to be different, okay? And then that is the instantaneous velocity at any given moment, okay? And then if you take the derivative again, you get the acceleration dv dt, and you end up with that one going away, and you end up with minus 30 meters per second squared times t. Uh-oh. Now the time is still there. The time is in there. That means the acceleration is not constant, but the time will change what the acceleration is. That's going to be kind of weird. If I threw another term in there, a t squared term in there, you might have the acceleration start off being positive, but then the acceleration being negative. Can you see in calculus class? You'd have to take the derivative and see when the acceleration was 0. Take the derivative and set it equal to 0. When's the acceleration 0? That's when this happens, when the velocity is a maximum, right? But then the velocity slowed down because the acceleration had a cubed term on there. So you can get lots of questions on at what time t is the greatest displacement, or where's the object when the acceleration was 0? You can have all these questions on there, but just refresh your memory on how to take all these derivatives so you get to a point where you can answer any questions I might give you. And remember, if I ask you for maximum or minimum, you just take the derivative of what I'm asking you for, set it equal to 0. And hopefully now you know, from a physics point of view, why that works. Okay? So hopefully that helped. And we're on to new and more exciting things in that chapter soon.